Assalamualaikum and hi everyone. So for today, we would like to present our topic for CHM361, which is crystalline solids. Before we begin, let me introduce the members of our group. So our group members are Fatin Hayati, NURUL ASYIQIN, ALIA SHAFIQAH, Shifa INSYIRAH, and also myself DARSAH AMNI. So first, let's move to the objectives. The objectives of this presentation are to describe the nature and characteristics of crystalline solids, and then to explain different types of crystalline solids based on bonding and also structure, to discuss various crystal structures and unit cells, and last but not least, to identify and explain defects present in crystalline solids. Next, crystalline solids are solids in which atoms, ions, or molecules are arranged in a consistent, long-range repeating pattern to give the solid a uniform structure. Okay, so most of the solid substances are crystalline in nature. The regular arrangement of particles forms a crystal lattice, which are responsible for many physical properties such as sharp melting points, hardness, and anisotropic behavior. So let's move on to the crystal structure. Crystal structure refers to the three-dimensional arrangement of atoms, ions, or molecules in a crystalline solid. These particles are arranged in a regular and repeating pattern known as crystal lattice. Okay, so according to chemistry, Liebert text, these orderly internal arrangements results in crystals having definite shapes, characteristic angles between faces, and also sharp melting points. The crystal structure play an important role, especially in determining the physical properties of a solid, such as hardness, density, and also cleavage. A unit cell is the smallest repeating unit of a crystal lattice that represents the overall structure of the crystal. So when this unit cell is repeated in all three dimensions, it will form the entire crystalline solids. So based on the chemistry Liebert text again, a unit cell contains all the essential information about the arrangement and also the symmetry of the particles in the crystal. Okay, so different types of unit cells exist, such as simple cubic, body-centered cubic, and also face-centered cubic, and these affect how efficiently particles are packed in the solid. With this understanding of crystal structure and also unit cell, we can now move on to the different types of crystalline solids and their properties, which will be explained by the next presenter.
Let's continue with the first type of crystalline solid, which is metallic solid. A metallic solid is the simplest type of crystalline structure consisting of identical metal atoms arranged in a regular lattice. These atoms are held together by metallic bonds where the bonding electrons are delocalized and move freely throughout the entire crystal, forming a sea of electrons around positively charged metal nuclei. This mobility of electrons allows them to move easily within the structure, making metal excellent conductor of heat and electricity. First, I will explain the crystal structure of chromium. Chromium has a body-centered cubic or BCC, crystal lattice structure at room temperature. As shown in the diagram, the BCC structure consists of chromium atom positioned at each of the 8 corners of the cube, with one additional chromium atom located at the center of the cube. In this arrangement, each unit cell contains a total of 2 atoms. The coordination number of chromium in a BCC structure is 8, which means that each chromium atom is surrounded by 8 nearest neighboring atoms. This specific crystal lattice arrangement contributes to chromium physical properties. The BCC structure gives chromium high strength and hardness, making it suitable for applications that require durability and resistance to wear. Next one is aluminium. Aluminium crystallizes in a face-centered cubic, also known as an FCC. In this arrangement, aluminium atoms are located at the 8 corners of the cube, as well as at the center of each of the 6 faces. In an FCC unit cell, each corner atom contributes 1/8, while each face-centered atom contributes 1/2. Altogether, this results in a total of 4 aluminium atoms per unit cell. The coordination number in an FCC structure is 12, meaning that each aluminium atom is in contact with 12 neighboring atoms. This dense atomic packing is responsible for aluminium physical properties. It makes aluminium malleable and ductile, and also allows it to conduct heat and electricity efficiently, which is why aluminium is widely used in many industrial and everyday applications. The last one is zinc. Zinc crystallizes in a hexagonal closed pack or HCP. In this structure, the zinc atoms are arranged in repeating layers. Each hexagonal layers contain atoms arranged closely together, and a third layer fits into the gap of the layer below, forming a compact and stable arrangement. In an HCP unit cell, there are a total of 6 atoms. The coordination number for zinc in this structure is 12, which means that each zinc atom is surrounded by 12 nearest neighboring atoms. Although the HCP structure is densely packed, it allows fewer slip systems compared to FCC structure. As a result, zinc has moderate strength and less ductile when compared to FCC metals. This crystal structure directly influences zinc's mechanical properties and its practical application. Next, I will explain the properties of metallic solid. First one is high melting and boiling point. Metallic solids are held together by strong metallic bonds. These bonds are formed by the electrostatic attraction between positively charged metal ion and a sea of delocalized electrons that move freely throughout the structure. Because these metallic bonds are very strong, a large amount of energy is needed to break them. As a result, metals such as chromium, aluminium and zinc require high temperature to melt or boil, giving them high melting and boiling point. The second property is electrical conductivity. In metals, the valence electrons are delocalized, which means they are not fixed to one specific atom. Instead, these electrons are free to move throughout the metallic structure. When an electric potential is applied, these free-moving electrons can flow easily, allowing metals to conduct electric current efficiently. This is why metals are good conductors of electricity in both solid and molten state. Because of this property, metals such as copper and aluminium are widely used in electrical wiring and electronic components, as they allows electricity to pass through them with minimal resistance. The third property is metallic luster. Metals appear shiny because of the presence of delocalized electrons on their surface. These electrons are able to interact with incoming light by absorbing and then re-emitting electromagnetic radiation. This interaction causes most of the light to be reflected rather than absorbed, which gives metal their bright and shiny appearance. This characteristic shiny surface is known as metallic luster. Because of this property, metals such as gold, silver and aluminium foil have a reflective surface and are commonly used in jewelry, decoration and reflective materials. The last property is malleability and ductility. Metallic solids are malleable, which means they can be hammered into thin sheets, and they are also ductile, meaning they can be drawn into wires. This property is due to the structure of metallic bonding. When a force is applied, the layer of positively charged metal ions are able to slide over each other without breaking the metallic bonds. The sea of delocalized electrons continue to hold the metal ions together, maintaining the overall structure of the metals even when it is bent, hammered or stretched.
So, what is an ionic solid? Ionic solids are formed when ionic compound is arranged themselves into crystalline structure due to strong electrostatic attraction between the oppositely charged ion. In the crystal lattice, each cation is surrounded by an ion and vice versa, which keeps like charges apart. This regular and repeating arrangement produces a highly stable structure as a result. Ionic solids do not exist as individual molecules but as extended three-dimensional lattice. So, sodium chloride or NaCl is a classic example of an ionic solid. In the solid state, NaCl does not exist as individual molecules. Instead, it forms a three-dimensional crystal lattice with face-center cubic or FCC arrangement. In this structure, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is also surrounded by 6 sodium ions. This is known as 6-to-6 coordination. This regular and repeating arrangement of oppositely charged ions create a strong electrostatic attraction throughout the lattice. As a result, NaCl has high lattice energy, which explains why is it hard, stable, and has high melting point. Ionic solids generally have high melting and boiling points because a large amount of energy is required to overcome the strong electrostatic attraction between oppositely charged ions. In the crystal lattice, for example, sodium chloride has a melting point of 101 degrees Celsius and a boiling point of 1413 degrees Celsius. This is because the sodium ion is relatively small, allowing it to be closer to the chloride ion. The shorter distance between the ions result in stronger electrostatic attraction and higher lattice energy. Compared to cesium chloride, NaCl has higher melting and boiling points. Although both are ionic compounds, the cesium ion is much larger than the sodium ion. This increased ionic size weakens the attraction between Cs plus and Cl minus ion. As a result, CsCl has lower lattice energy and requires less energy to break its crystal lattice, giving it lower melting and boiling points than sodium chloride. Ionic solids are generally hard but brittle due to the strong electrostatic attraction between oppositely charged ions in the crystal lattice. These strong ionic bonds make the structure rigid and hard. However, when a mechanical force is applied, layers of ions in the lattice may shift slightly. This shift causes ions with the same charge to come closer together, resulting in strong electrostatic repulsion. The repulsion causes the crystal lattice to crack or shatter along the smooth planes rather than bend. Therefore, ionic solids are brittle instead of malleable. In the solid state, ionic compounds do not conduct electricity because the ions are fixed in a position within the crystal lattice and cannot move freely. Since electrical conductivity requires the movement of charged particle, the lack of mobile ion prevents the flow of electric current in solid ionic compounds. However, when ionic compound is melted or dissolved in water, the crystal lattice breaks down and the ions become free to move. This mobile ion can carry electrical charge, allowing ionic compounds to conduct electricity in the molten state or in aqueous solution.
Next, we move on to the covalent solid. A covalent solid, also known as a covalent network or giant solid, is a type of crystalline solid in which atoms are arranged in a regular repeating pattern. In these solids, atoms are held together by a continuous network of strong covalent bonds. They are made up of non-metal atoms and the entire structure forms one giant molecule rather than individual molecules. Covalent solids are often found as allotropes, which are pure forms of the same element that differ in structure, such as diamond and graphite. Next, I will explain the structure, properties and uses of the diamond. So, what is the structure of the diamonds? Diamond has 3D giant covalent structure and each carbon atom forms 4 strong covalent bonds with 4 other carbon atoms in a tetrahedral arrangement. This creates a rigid and continuous network of covalent bonds that extends throughout the entire crystal. How about its properties? One of the properties of diamond is it does not conduct electricity because there is no free or delocalized electron available to move. Diamond is also extremely hard because strong covalent bonds are present in all directions within the 3D structure. In addition, diamond has a very high melting point, about 3550 degrees Celsius, due to its giant covalent structure. So, do you know the uses of the diamonds? Because of its extreme hardness, diamond is widely used in cutting tools, drilling equipment, and grinding materials. And some will also use diamond as an accessory or jewelry. Enough about the diamond. Let's move on to the next part, which is graphite. So next is graphite. Graphite has a layered covalent structure. Its carbon atom is covalently bonded to 3 other carbon atoms forming 6 membered rings. These rings lies in the flat 2-dimensional layers. The layers are held together by weak van der Waals forces, making the overall structure less rigid than diamonds. So, how about its properties? Graphite can conduct electricity because each carbon atom uses only 3 of its 4 valence electrons for covalent bonding. The remaining electron become delocalized and it's free to move along the layers, allowing the graphite to conduct electricity. On the other hand, graphite is soft and slippery. Although the covalent bonds within each layer are strong, the forces holding the layers together are weak van der Waals forces. Not only that, graphite also has very high melting point, similar to the diamond. So, do you guys know the uses of the graphites? Graphite is suitable for use as space and lubricants. Next, I'll talk about our next objective, which is crystal defects. So, crystal defects. Crystal defects are irregularities in the arrangement of constituent particles in a crystalline solid. This deviation from perfect order are called defects or imperfections. There are 2 types of crystal defects, stoichiometric and non-stoichiometric defects. I will talk more about the stoichiometric defects. Stoichiometric defects are small irregularities in the crystal structure where the ratio of cations and anion remains unchanged. Next, we will move on to the examples of stoichiometric defects.
Vacancy defect occur when an atom is missing from its regular lattice site. Because atoms are missing, the density of the substance decreases. Next is interstitial defect, which occur when an atom occupies a site that is not normally occupied, which located at a space between regular lattice sites. Because extra atoms are present while volume stays similar, density increases. Third is the Schottky defect, which occurs in ionic crystals such as sodium chloride and ACl when a pair of 1 cation and 1 anion are missing from their regular lattice site. This decreases the density of the crystal. The last one is Frankel defect, which occurs when a smaller ion, usually a cation, such as Ag+ from silver chloride, AgCl, leaves its regular site and moves to an interstitial site. Since no ions leave the crystal, the density remains almost unchanged. Next, I will explain about non-stoichiometric defects. Non-stoichiometric compounds are compounds in which the proportions of anions and cations is not similar. These defects are known as non-stoichiometric. There are 2 types of these defects, which is metal excess defect and metal deficiency defect. Under metal excess defect, there are also 2 types of it, which is anionic vacancy and extra cations. Next, I will talk about one of the non-stoichiometric defects, which is metal excess. Firstly, I will explain about anionic vacancies. Anionic vacancies is where an ionic solid has a defect, where an anion missing from its lattice site, leaving a hole occupied by an electron. The trapped electrons are known as F centers and color centers because it's responsible for imparting colors to the crystal. Next, metal excess, which is extra cations, is where a metal excess defect in an ionic solid, where extra positive metal ions, cations, sits in an interstitial space within crystal lattice, while electrons occupy another interstitial site to maintain electrical neutrality. Next type of non-stoichiometric defect is metal deficiency defect. In this defect, some cations are missing from its lattice site to maintain its electrical neutrality. One of the nearest metal ions acquires 2 positive charge. In conclusion, crystalline solids are materials which particles are arranged in regular and repeating patterns. The type of bonding and crystal structure determines the physical properties of a solid, such as hardness, melting point, and electrical conductivity. Different crystalline solids, including metallic, ionic, and covalent network solids, exhibit unique characteristics based on their structures. Additionally, the presence of crystal defects shows that there is no perfect crystal, and these defects play an important role in influencing the properties of solids.